from Professor Samuel Poncé from the University of Epw Code, who's going to cover current transport. Using and he will tell you a bit about how these things are done and how we do it with Ew. Then there's going to be Professor of Martin talking about protonactivity, and then after the coffee break, there's going to be Professor Juan Tupakis talking about phone-assisted optical approach. Okay, so first presentation by Samuel Poncé on current transport.
Thanks a lot, Feliciano. So for this lecture, I'll be talking about carrier transport. So this is a topic that I'm very keen on, I really like. And so the idea for this lecture is I will first sort of discuss briefly the different kinds of carrier transport, charge transport. And then what I will try to do is to show, so basically building on what Feliciano showed yesterday, about field theory and quantum many-body framework, I will try to show how you can do some approximation to obtain the Boltzmann transport equation. And so that will be quite a bit of math, but let's say what's important is to understand the key ideas and the key approximation to get this Boltzmann transport equation, because that's what we're going to use in the afternoon for the hands-on session. And then I will sort of show some example on simple bulk, realistic bulk semiconductor and the mobility. And then I will discuss what happened when you apply a magnetic field, and then you get the whole mobility and how to extend the Boltzmann transport equation to include that. And I will sort of finish with this extension to metals, so how to compute resistivity in metals. Okay. Yeah. Okay. So basically, like I said, there are different ways in which charge can propagate in the materials. So you can have a density gradient in which case the particle will just move. That's a fixed law, and this is called diffusion. So that's one way for charge. And so when I will talk about charge particle, I will refer to as the electrons or the hole. You can have a temperature gradient, in which case you get thermoelectricity. And you can have phonon drag. So what is happening is that as you have a heat gradient, the lattice will deform, and this will sort of, the lattice will carry charge with them. And so you will have electron that will move from the hot source to the cold one. And then you have, Seebeck effect and so on. And the last one is what happens when you apply an external electric field. So when you apply a field, you have drift current. So what's happening is that you apply an external field, and then the charge will start moving as a result of that applied external field. And the movement of those charge in all those cases can be reduced by different scattering mechanisms. So here I list some of them. You have Electron-Phonon or lattice scattering, ionized impurity scattering. So this is the case when you have a lot of carrier, when you have a lot of charge particle. They will sort of interact with each other. So the particle will move, and then the one that's coming after will sort of feel the movement of the first one. And this typically reduces transport. You can have alloy scattering or defect scattering. So if the material is not pure, then of course this will also typically reduce mobility. And so in this presentation, I will focus on the last case, so the drift mobility. Okay, so the idea is that I want to start from this very general many-body framework, in which you can define the current density in terms of this gradient of this lesser Green's function. So yesterday, Feliciano introduced the Green's function in terms of field operator. So those are time-dependent Heisenberg field operator. And so you can see the Green's function as a propagator. So you have a particle that you create, and it propagates to this time 1 to this time 2, and so on. And so you can also include temperature through this thermodynamical average. Now, the issue is that you want to compute this Green's function. So if you want to solve for the current density, what you need to do is you need to solve the Green's function. And so in that context, what is really difficult is that your Hamiltonian, you can see it's both in this exponential, but it's also in the denominator, and therefore they will not commute. And so it's quite difficult to solve this equation. And so what people typically do is that they recast this Green's function on what they call a contour. And so the idea is that instead of having a real time, you now have a complex time on this plane, and you have this complex leg. And the idea is that on this contour, then things can commute, and therefore it's much easier to solve. And so the idea in most cases, when you want to solve the Green's function, is to use perturbation theory. So you want to expand this Hamiltonian in terms of a non-interacting one, and then an interacting one, and one coming from the external potential that you're applying. So for example, this external field. And so what you can do is you can do a perturbative expansion, a Taylor expansion, in terms of this interacting Hamiltonian. And so you get your Green's function that can be expressed as a non-interacting Green's function. And this non-interacting Green's function is just the product of those field operator. And then you have this Taylor expansion. And the idea is that you can express all those Hamiltonian in terms of field operator. And then you have something called the Wick's theorem. And the idea is that then it allows you to express all those Green's function in terms of product of non-interacting Green's function. And therefore, you can then express them in terms of Feynman diagram, and you can solve this infinite Feynman diagram series. And this gives you the Dyson equation that you might be familiar with, because this is used in GW approximation. And so this Green's function, and now I'm using this notation where one refers to position and complex time. And so in this Dyson equation, you have this self-energy, which is hiding all this infinite expansion. And then the idea is that you have to, you can sort of massage a bit the equation. You can explicitly solve for the non-interacting Hamiltonian. You can use Lancret rule and so on. And you can evaluate this Dyson equation at equal time. And the reason you want to do this is because in the first slide, I showed that the current density was the lesser Green's function at equal time. So you want to look at equal time. And what you end up with is a series of 7 Kardanov-Baum equation of motion for all the Green's function. So the idea is that you are splitting this the full Green's function into different parts on this contour. So you will have a lesser, a greater, retarded, advanced, and so on, a Green's function. And for each of them, you get an equation of motion. And so here I'm only interested, and I'm only showing the equation of motion for the lesser Green's function, because this is the one we are interested in for the current density. And so what this equation tells you is that the change, the time-dependent change of this lesser Green's function is equal to those 3 terms. The first one is the unperturbed time evolution of this lesser Green's function in a static potential. The second one we call it the local time, because you can see that here the self-energy depends only on one time. And the last 4 terms corresponds to all the internal correlation, dynamic, collision, scattering, and so on. Okay, and so basically the idea is that this is the most general equation of motion for particles, this Kardanov-Baum equation. So far we have done no approximation. And the idea is that you see on the right, we will do several approximations in order to arrive to the Boltzmann transport equation. And so I will maybe skip some steps, but you can look at this reference, and all the steps are very clearly laid out. And so this allows you to go through. But what I will try to show is what are the key approximations that are needed in order to get the Boltzmann transport equation. So the first thing that we can actually notice is when you evaluate the non-interacting Hamiltonian, you can actually show that this term is 0, the first one. So you're left with the last 2 terms. And we can first work on this red term. And if you do those 2 approximations, you approximate the exchange correlation potential, and you can express it as in terms of the external field that you're applying. And if you assume that the external electric field is spatially homogeneous, and this is a very reasonable approximation, because in many experiments you will apply a big, external electric field, and so it will be spatially homogeneous. And then you can express this difference in terms of the external electric field and the position. And if you do that, then this term reduces to E, the position difference, and then this lesser Green's function. Now, the second thing that we can do is we can block project our equation. So the idea of this block projection is simply to evaluate this expression in those block wave function, and then we integrate. And so I'm defining here this block projection of the lesser and greater Green's function. And I'm defining this object, and this is actually the lesser and greater occupation function. And when this will be integrated later, you will see that this is really the occupation of the state, so the occupation of the electron and the hole. And so if you do that, then this expression is simply the E times dF lesser dk. So this can be shown because you have position, and so then when you transform, you get a derivative with respect to momentum. Okay, and so with those two sort of approximations, so yeah, I forgot to mention, when we do this block projection, the approximation that we need to make is that we are neglecting off-diagonal elements. So we are projecting in this sort of block basis, and we are only considering diagonal matrix elements. So this is the approximation. So with this diagonal approximation, and then those two, and then basically this first approximation, then we end up with this quantum Boltzmann transport equation, which is also sometimes called the AC Boltzmann transport equation. Why? Because we are retaining a time dependence. And so this would be the equation that you want to solve if you have an AC field, so you have an oscillating external electric field, then this is the equation that you want to solve. And so you can try to understand this equation. And so you have this, the change of this occupation function with respect to time, how this occupation evolve. And then you have, so this is nothing but the lesser Green's function. Once we block project, this is the Green's function. So you want to characterize how this Green's function evolve, how this occupation evolve. And then the red term is the driving term. So this is the term that basically makes the electron move. It's because of the field that you apply, then the electron will move. So this is the driving term. And then in blue, you have all the resistive terms. So this is the collision and so on that will reduce, that will make the electron go slower somehow. And so this collision rate, you can express it with those four terms that I mentioned. And here I'm introducing another notation, which is this gamma. And this is, again, the block projection of the lesser and greater self-energy. Okay, so now this is still relatively complicated to solve. And so what we can do is we can look at instead DC transport. So this is when you apply an electric field that does not change with time. So in this case, of course, the first term will vanish and you don't have time dependence anymore. And then you're left with those two terms. So you have the driving term on the left and the resistive term on the right. And because you are now not depending on this derivative on time, you can do a Fourier transform and you can work in the frequency domain. And then what you can do is you can integrate over the frequency, and then this gives you the occupation function. So this is the field-dependent occupation. So this is the out-of-equilibrium occupation of your state. So when you are in equilibrium, this F reduces to the Fermi-Dirac distribution function. Now, the last thing that we need to do in order to be able to solve this is to work on this gamma, so this block projection of the self-energy. And this is very difficult to compute. So we need to do a lot of approximation to be able to compute this term. So we will only consider lattice scattering. We will neglect phonon-phonon interaction. We will neglect the frequency dependent in the electron-phonon coupling. We will consider that the phonon Green's function is in the adiabatic approximation. And we will also consider this form for the lesser occupation function. And if you do all of that, then you end up finally with the Boltzmann transport equation. And so this is, again, on the left is the same driving term, but now on the right, you have an expression that you can actually compute in the code with perturbation theory, density functional perturbation theory. So this G is the electron-phonon matrix element that you saw yesterday, that you did in the hands-on. So this is really the electron-phonon matrix element. And then you have those four terms that are energy conserving term, and they correspond, so that the color corresponds and match to those four cases. So they correspond to electron leaving the state Fnk or entering the state Fnk by absorbing or emitting one phonon. So those are the four possibilities. And so keep in mind, these F, they are really field dependent. They are out of equilibrium F, and this is what we want to compute. So now if I go back to the current density, so this is now the macroscopic average of the current density. So I just integrate over position. And so again, this is the gradient of the lesser Green's function. And then when you do all this approximation, you do block projection and so on, this Green's function is nothing but this field-dependent occupation function. And this gradient gives you this velocity term. So this is the electronic velocity times this occupation function. And now in the case of weak electric field, you can use linear response. And actually, the definition of the conductivity is the change of this current density with respect to external applied field and you evaluate that at vanishing field. So this is the definition of the conductivity. And therefore, you get simply velocity times the change of occupation with respect to field. And here I'm introducing this notation. So basically, dE is nothing but just the derivative with F with respect to external field evaluated at zero field. Now, in practice, experimentalists, they like to work with mobility instead of conductivity when they are dealing with doped semiconductor. And the reason is that the conductivity will scale with the amount of doping, the amount of charge carrier. And so it's more difficult to sort of find what is really the intrinsic conductivity, the intrinsic transport properties of a material. And so they usually refer to the mobility, which is simply this conductivity divided by the carrier density. And therefore, this value does not change material. I mean, it's a constant value per material. It's really an intrinsic value of the material. And so this is the drift carrier mobility. Okay, so in practice, what we need to do is we need to compute this term. And I will make a small parenthesis just to be very clear. So if you then look at all this Berry phase and so on, what you actually find out is that this current density is the product of this sort of derivative of the position operator times this occupation function. And if you expand both of them, you get this. So this gives you the band velocity, but you actually have another term, which is called the anomalous velocity, where you have this Berry curvature. And then this term will give you, you can do a Taylor expansion of this term, you get the Fermi-Dirac plus other term, and they're expanded in terms of the electric field. And when you do all this multiplication, you get a constant term, then you get, by definition, this is the definition of the conductivity, is the proportionality constant between the current density and the field that you're applying. And then you have a higher order conductivity terms with respect to the field. And so your conductivity is this first term that I've been discussing so far. So this is this ohmic resistive term, which is this velocity times this occupation. But then you have a second term, which I'm not discussing now. And this is the term responsible from the anomalous, so the Berry curvature and so on. And so in system where you have time reversal symmetry, actually this term is zero. And so for the rest of this talk, I will assume that we are in the case where this term is zero. But you just need to be careful that if you are not in this situation, then you may need to compute that. And there are software that allows you to do that in 1 year. You have 1 year Berry and other software that can allow you to compute this quantity. Okay, so back. So now we are really only dealing with resistive transport. So now the idea is we want to compute drift mobility. We need to compute this change of occupation with respect to external field. And so to compute this, what we do is very simple. We go back to our Boltzmann transport equation. And then what we do is we derive on both sides with respect to field. So the first term, this will die. We are just left with this term without the field. And then the second, the right-hand side term will have many derivatives, partial derivatives, so derivative with respect to field for all of those quantity. Then you need to rearrange all of them. And then you get basically this equation. And so then you put on each side. And so what you get is that this quantity, F and K, actually depend on this term, which here I've introduced this scattering rate, which is expressed in terms of the electron-Phonon matrix element. But then you have also this term, and you can see that the same change of occupation with respect to field also appear here, but now you have K plus Q. And so one way to solve this is to solve it iteratively. So this is sometimes called the iterative Boltzmann transport equation. So you have to plug an initial guess. Typically, you cancel this term, and that's the initial guess for this one, and then you solve this iteratively. Now, if you don't want to solve this iteratively, you can just decide to cancel the second term here, and then this is what we call the self-energy relaxation time approximation, because you can now express the mobility in terms of the velocity times this occupation function, but now this occupation function is directly linked with only this scattering rate, and actually this is the same as 1/2 the imaginary part of the self-energy. So you now have a direct connection between the mobility and the imaginary part of the electron-Phonon self-energy. So this is why we call it the self-energy relaxation time approximation. Yeah, and so this is the most approximate way for this Boltzmann transport equation. Okay, so now you can see that it's sort of a difficult object to compute because you have a double integral. You need to integrate in K points this object, but actually this object you also need to integrate in Q points. So you have this double integral to perform. And as Fritzano presented, in practice, because of all this energy conserving delta, what is happening is that only the state very close to the band edge will contribute. And you need to describe them very well in case of doped semiconductor or semiconductor. And therefore, you need very, very dense grids to be able to describe them. And so the approach that we've been taking is to use the Epw code. And so we compute quantities on a coarse grid, such as the electron-Phonon matrix element, but also the dynamical matrices and so on. And then we Fourier transform them into real space using the 1E90 software to be maximally localized. And when we are localized, we can then do a Fourier interpolation of those matrix elements on very, very dense meshes. Now, the small technicalities for this is that if you have a infrared active material, you start having long-range electrostatic field, and therefore this prevents you to do a good interpolation because your quantity will not be localized in space. And this has been discussed already a bit yesterday. And so the strategy is to subtract this long-range term, which you can evaluate sort of analytically, and then you add it back. So then you do what you interpolate is the short range of the electron-Phonon matrix element. And this long range can be expanded into dipole, quadrupole, octopole, and so on. And each of those terms, they look relatively complicated, but actually you have all the ingredients. If you do a DFPT calculation at the gamma point, you get all the quantities. You have the Born effective charge, you can have the quadrupole tensor and so on, the electric function, and then you have this expression that you can subtract to your matrix element and then add back. Now, for a relatively long time, one was only subtracting the dipole term, the Fröhlich term, but it's been recently pointed out that actually quadrupoles are important. So for example, in silicon, you don't have Fröhlich term, you don't have dipoles, but you do have quadrupole. And this is an example of the electron-Phonon matrix element for a specific band in silicon. And you can see this is so the x-axis is the Q point. So I'm looking at a specific K point, and I'm now changing the Q points. And what is happening is the dots that you see are direct DFPT calculations. So you make no interpolation. And then you are comparing that with interpolated value using this scheme. And if you don't include quadrupole, then you get those gray lines. So you see that they go to 0. Whereas in reality, you really need those quadrupole to describe those non-analyticities. So as you are coming to gamma, you have different value of the matrix element. And so in that case, for that particular mode, quadrupole are quite important. And the last technical bit is that you need to obtain the carrier velocity. So when you want to compute the mobility, the two ingredients that you really need is this carrier velocity and then this change of occupation function. And so there are two ways that are both implemented in EPW and that we will discuss further this afternoon to compute the velocity. The first one is directly from this commutator relation. So you can show that this is equal to the momentum operator plus the commutator between the non-local part of the potential and the position operator. And this can be solved by solving a linear system. So this is a bit similar to the Sternheimer equation. And if you don't want to solve this, you can also neglect this non-local part, and then you get the velocity in the what we call the local approximation, where you neglect this non-local part and you only compute this momentum operator, and then it takes a very easy, simple form to compute. But of course, it's more approximate. So this direct solution is better. And the reason is that most pseudo-potential nowadays have a non-local part, almost all of them. And therefore, it's much better to use this. The alternative way is to use a one-year function expression of the velocity. And so this top expression from this paper, you can express the velocity in terms of the Hamiltonian and this Berry connection. And this Berry connection can be rotated into this one-year space using those smooth block one-year rotation. And then this can be expressed in terms of computed in terms of finite difference with this formula, where what you can see is that here you have the overlap of the periodic part of the wave function in this one-year space. And then this can be expressed in terms of this M&M that you've done yesterday with the one-year tutorial. And so this M&M is computed by an ab initio software. So for example, Quantum Espresso. And so this is the overlap, the phase relation between very close K points. So this is K plus B, and B is a K point very close to the points that you are looking at. So this sort of tells you the phase and the smoothness about as you move through the K points. And so you just with this information and the one-year rotation matrix, you can then obtain the velocity. So this is the second way to compute the velocity. Okay, so does this work? Does this Boltzmann transport equation work? So here are some results for 10 simple semiconductors. So you have diamond, silicon, it's quite small, but you basically have gallium arsenide, silicon carbide, aluminum phosphate, etc. And for each of them, I'm showing the electron mobility and the hole mobility as a function of temperature between 100 and 500 Kelvin. As what you can see is that in all cases, what is happening is that as you increase the temperature, you get more scattering. And so the mobility will always decrease with temperature. And you can see that you have this decrease in all cases. And you can also see that it compares quite well with respect to experiments. So all these dots are different experiments, experimental data. And in general, we are overestimating experiment, and there are very good reasons for that, because we are only considering electron-phonon scattering. But of course, in a real material, in an experiment, you will have other forms of scattering. What is also quite nice with this framework, with this implementation, is that you can do spectral decomposition. So what I'm doing here is I'm looking at the phonon frequency, and I'm looking at the contribution of each mode to the scattering rate. And from the scattering rate, in this Certa approximation, this is directly linked with the mobility. So the mobility is proportional to the scattering rate. And so here, you really see that, for example, those four materials, they are really dominated by acoustic scattering, so all of them. And it sort of makes sense because those are very stiff, material, cubic boron nitride, diamond, silicon carbide. And then you have some sort of very polar material like gallium arsenide, aluminum arsenide, and so on, that are dominated by optical scattering. But then you also have materials where both are important. So you really need to account for all those different types of scattering. And this is all done ab initio, so you don't have to have specific models for each of them. So for example, it's possible to describe acoustic scattering with deformation potential theory, or optical scattering with some other model. But here it's all included in directly ab initio. Okay, and so for those 10 materials, but so I have electron and hole, so this is 20 cases. You can look at the comparison between calculated mobility versus experimental mobility. So if you are on this dashed line, you have perfect agreement. And you can see that most material are on the right side, which means that the calculated mobility is overestimated. So the result I'm showing are the drift mobility in the Certa approximation, but I can also solve the equation iteratively, and then I get the PTE mobility. And you can see that in most cases, it increases the mobility a bit in all cases. Now, in practice, like I said, you can do those experiments with time of flight. So those are drift experiments, but they are very difficult to do experimentally. And so what typically experimentalists do is they do hole mobility. So what you can do is you can apply a magnetic field orthogonal to your sample. So you have the electric field like this and the magnetic field, which is orthogonal. And what is happening is that the carrier gets deflected due to Lorentz force. They will be deflected to one side of the sample, and then you can measure the change of potential. And this gives you the hole mobility. But of course, the problem is that you're accelerating the electron, or at least changing sort of their velocity due to this magnetic field. And so you have something called the hole factor. So the hole mobility is the drift mobility that you've seen before, but you have to multiply by this hole factor. And the hole factor does not depend on the magnitude of the magnetic field, but it depends on the direction. And so it's really in the limit of vanishing magnetic field, you have this ratio between the mobility computed with magnetic field and the drift mobility. And so one can also compute the mobility with magnetic field. And so you can see that to obtain this, you need this change of occupation for a finite magnetic field when the magnetic field goes to 0. And so what you can do is you can augment your Boltzmann transport equation to account for this additional driving term. So the magnetic field is another driving term. And so this is this new term that you can see here, where you have this magnetic field cross V. And then you also have this derivative with respect to K. And so you can basically now solve this Boltzmann transport equation with magnetic field. And this gives you then the hole factor. And then you can also have this new result, which is the hole mobility compared to experiment. And you can see that in most cases, it increases even more the mobility, but there are cases from like this one, where the Hall factor is actually smaller than 1, so you are reducing the mobility. So an important message is that the Hall factor is not unity. And so there are many experimental or papers where this is assumed, but in some material it might be good, but in most material it's not. And so if you really want to compare to experiment, you need to be careful to include it if it is a Hall measurement. So you can see that it's also temperature dependent. So for example, in all those material, the Hall factor increases, in some it decreases, and in some it's relatively temperature independent, but still the value can go quite high. So it's important to compute the Hall factor, is the message. Okay, and then this last part is about the resistivity in metals. So now we've seen semiconductor, doped semiconductor, but now we want to also be able to describe metals. And the theory is very similar. So now we are interested in resistivity and not mobility anymore, because in metals, you basically have the Fermi level and you don't really have control over the charge carrier, the number of carrier. And so in this case, what you can do is you can solve the Boltzmann transport equation and obtain the conductivity the exact same way that we've been doing for the semiconductor. But I just want to present an approximation because it's relatively common in the literature, and it's called the lowest order variational approximation, or the Siemens formula. And you are basically taking the Boltzmann transport equation and you are doing two additional approximations. You are considering that the electron-Phonon matrix elements are relatively constant close to the Fermi level, and you're also doing this sort of delta approximation. And if you do that, then you can recast the conductivity in this quite nice form, where you can see that it's now expressed in terms of this isotropic Eliashberg transport spectral function. And in the next talk by Roxana, she will certainly talk more about the Eliashberg theory, because this is a bit linked also with superconductivity. But so this is the transport version of the Eliashberg spectral function. And so what you can see is that this one, if you want to compute, you need to compute the mode result transport coupling strength. And then the typical coupling strength without transport is just this term here is 0. So you have just 1. So what is this term? It's just the electron-Phonon matrix element, and then you have two delta function, but you can see that they are with respect to the Fermi level. So this means that you are only considering the state very close to the Fermi level. Okay, does this work? Yeah, so this is lead. And so this is the difference between the transport and the normal Eliashberg spectral function. And you can see that they are relatively close. So this is the comparison between the dash and the plane line. But what really matters in lead is whether you include spin-orbit coupling or not. Because in lead, it's a very heavy material, and therefore you sort of want to have spin-orbit coupling. And so if you use that spectral function that I showed you, then you obtain this resistivity as a function of temperature. And so this match experiment quite well. And then you can compare this Siemens formula with a direct calculation of the Boltzmann transport equation, and you get sort of similar result. Okay, so this is more or less what I wanted to present, and I want to just finish on presenting a few direction, a few flavors of where I think the field is going and what could be, included in the calculation to make them more accurate. So one could include anharmonicities, because the phonons are not always harmonic. One can consider non-adiabatic phonons, because so far we've been considering adiabatic one. You can take into account renormalized band structure. So this was touched upon yesterday, but due to electron-phonon coupling, you can have renormalized state or spectral function. You can have two coupled Boltzmann transport equation, because of course the Boltzmann transport equation also applies to the phonons. So you also have an equation of motion for phonons, and you can solve them both. So you can solve the equation for phonons and the equation for the electrons. You can consider other scattering mechanism. So here they considered electron to phonon scattering. In what I showed, we assumed a low electric field, but you can also consider the high field regime. And actually, this is both for the electron high field, but also the magnetic high field. So you can also try to see what happens if you apply a very high magnetic field. So in that case, it's much more difficult to describe. You will get Landau level and so on. And then you can try to describe ab initio electron defect scattering or other scattering mechanism, ionized impurity, and so on. And so I will just show for each of those directions that I think are important, but there might be other direction, of course. I will just show a few work that I think are relevant. So in those work, they did not always apply it to transport, but I think it would be interesting to basically apply those to transport. So for example, for anharmonicities, there is this theory called SS-SHA theory. And this is a way, fully ab initio, to compute anharmonicities. And you can see that in some materials, you have very strong soft phonons. And so if you then, so in this case, it's these hydrides that are used for superconductivity. And if you use anharmonic theories, then you manage to stabilize them. And therefore, you can then use them in those transport theories. Because when you have soft mode, then the theory, the Boltzmann transport theory is not very well defined. So you would prefer, you would like to have a sort of positive modes. For non-adiabatic phonons, so this is basically diamond. And if you dope it quite heavily, so this is boron-doped diamond, what is happening is that you have a softening of the mode, and you have also this broadening. So what is it? What is this thing? It's simply the phonon spectral function. So this is similar to the electron spectral function, but for phonons. And so you are renormalizing your phonons. And so this is the equation for that. And you can have softening, you can have broadening, and so on. And so what one can and already do compute this phonon spectral function, but to my knowledge, it's not been used in the framework of transport. But you could basically replace your phonon frequency by those renormalized one and see how that affects transport. So again, this is relatively similar, but now you are changing the electronic band structure. So again, due to electron-phonon interaction, you get something called the 0-point renormalization. So this is even at 0 Kelvin, the band structure will be renormalized and there will be some broadening. So this is the case of diamond at 0 Kelvin. You can see that this band structure decreases a bit, so the band gap reduces. And if you increase temperature, it will reduce even more, and it will broaden even more. But so you could basically just renormalize the cone sham band structure or the GW band structure using electron-phonon interaction, and this will typically change a bit the result. The gap is really not important for transport. What really matters is sort of the effective mass. That's what's really important. And so if you are renormalizing your state, and this is k-dependent renormalization, therefore you could change the effective mass, and this is the whole mass enhancement and so on that you can observe. And so one would expect that this has an effect on on mobility, because typically that makes the effective mass heavier, and therefore it might reduce a bit the mobility, and so we could be closer to experiment, because as I showed, in some cases we are maybe twice the experimental value, and so taking those effects into account can bring us closer to experiment. And something even more refined, this is from Carla and Ficciano and so on. They did very nice study using a spectral function. In that case, you can add many more physics. So you can do accumulant expansions, you can have satellites, you can have plasmons, you can have many other physics, and you could, in principle, do a theory of transport using spectral function instead of using well-defined quasi-particle. This is the coupled equation I was mentioning. So this is a very recent work by, I think, Nakib Protik, where he managed to basically solve the coupled Boltzmann transport equation. So this is the electron Boltzmann transport equation that I showed, but there is a similar one for phonons, and you can actually solve them self-consistently. And then this gives you thermal power and things like that, and you can also include drag. So that's very nice direction, I think. If you include higher order scattering, so this is electron 2 phonons, but you could also have electron 3 phonon. You can have two. I mean, there are many different scattering you could consider. But apparently, here in the case of gallium arsenide, by including electron 2 phonon scattering, you significantly reduce the mobility. So you go from this line here, where you have the normal, so ITA is the iterative Boltzmann transport equation, and you go from this line to the one here if you include 2 phonons. So you drastically reduce the mobility, and so in some cases it's very important to reproduce experiments. So now, if you are not considering this low field regime, but you are going to a high external electric field, then you have this study where they looked at sort of bigger but not very big electric field and how the DC mobility was changing or reducing as a result of this high field. Yeah, and then finally, the last topic, which I think is quite important, is to calculate from ab initio the effect of defect scattering. And this is sort of a first version where I think they consider only neutral defect, but one can extend this to also not neutral defects or charge defects and so on. And they have like this framework to compute this ab initio, and I think that's also an important route to go, as well as describing ab initio ionized impurity, which is also done here in the group. Okay, so with that, I'm done. And so the take-home message is that the Boltzmann transport equation can really be obtained starting from a fully many-body framework. So it's not a phenomenological equation. It's really something you can show that starts from this very general many-body framework, and then you do a number of approximation, and then you obtain this Boltzmann transport equation. And so if we want to go beyond, we can try to remove some of those approximations and try to be more accurate. I would like to emphasize that the long-range electrostatic is very important if you want to do accurate interpolation. So including dipole, quadrupole, and so on, to do this properly is very important if you want to accurately interpolate those quantity. And I want to emphasize also that computing mobility, this is really a quantity that is almost impossible to do without interpolation. So you have to compute so many matrix elements that you really need to require some form of interpolation. And therefore, treating that properly is important. The whole factor is something that is temperature dependent and can deviate strongly from unity. And therefore, I think it's really important that one computes that if one wants to compare with experiment. And in general, for now, the BT mobility sort of overestimate experiment, but that's expected. And I think adding more bits will bring us even closer to experiment, but I'm not too worried about this. Okay, that's it.
Thanks for the presentation. I was wondering if you start off with the Dyson equation, if you can derive equations for the transport of localized carriers.
So this I haven't. So you Polaron and so on. So this will be discussed, I think, on Thursday. But to my knowledge, I don't know if it's directly derived. You can derive it directly from here. I guess yes, but I haven't done it myself. So I don't know. I mean, what we've done as well is to look at the Kubo transport formula. So you can also connect with this ballistic Büttiker and so on. So this definitely stems from this as well. And you can show those two lines, and you can show how with some approximation they connect to the same thing. So this we've done, but localized carrier we haven't done. So I wouldn't be able to comment very much on that. But I would guess it could, because this is as general as it can be. So I guess yes, but I don't know where or which approximation would be needed to describe them accurately. But there will be a session about Polaron. So yeah, that will answer.
Just wondering how the spin enters the calculation. So I assume that the velocity and the scattering rate are spin dependent.
Yeah. So basically, currently you can, for example, use spin orbit coupling. That's not an issue. But you cannot at present. You cannot do magnet. I mean, in theory, you could. There is no issue. The only problem is that you would need to compute the electron-Phonon matrix element, which is both spin resolved and also with magnetic effect, for example. And this could be done in principle. It's just that it's not implemented, at least in quantum espresso, with magnetism. And so this is something that then one could extend. And so instead of having a G, you would have I think a 2x2. So you would have up, 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 down, down, up, and then you just need to solve this slightly more complicated equation. And then you have spin-off for the wave function. So I think that wouldn't be an issue. So we already have spin-off for spin-orbit coupling. It's just that at present we cannot treat magnetism, basically. But this would be possible if it becomes available in DFT software that we are interfacing with. But there is no issue. And indeed, it's very Those results are with spin-orbit coupling. So you have two bands basically for each, and you don't assume that. So you treat them separately. So you really have, so basically the electrons are different. Yeah, no, you don't assume they are the same. But you can also do this calculation without spin-orbit coupling, and in that case, you would assume that they are the same.
Thank you. So on slide 8.
Sorry?
You mentioned the approximation where you only use the diagonal elements.
Yeah, this is exactly what's written. Okay, if no, not strong band mixing. So yeah, so that wouldn't be okay. I agree. So in case where you have strong band mixing, this approximation would not be very good. So it's just that at present we don't have a good way to deal with that basically. But that would be an interesting direction to go and trying to generalize this to include that information. But yeah, at present with what we are able to compute, we need to do this approximation. Yeah. So it's just, I mean, it doesn't have to be, but it's what we've been doing so far. And it's working quite well for, simple semiconductor and so on. But I agree that there might be a system in which this might fail. Totally agree. Yeah.
Where of any
specific materials in which it fails?
Yeah.
I guess like very small band gap, for example. So some material, yeah, that might be a problem. Yeah. Yeah. So we purposely didn't look at those. Yes. But yeah, I mean, so this is all relatively new, this implementation and so on. So we are still trying to figure out sort of simple systems. But definitely, I mean, those are the direction that are very interesting to look at, I think. Yeah. Definitely.
Hi, thank you for the talk. I have a very similar question, but about a different approximation. Because I noticed that you assume adiabatic phonons, which at first sight seems like a very drastic approximation to me. So my question is it drastic, or is it just very good in most materials?
So, I mean, we haven't tested without this approximation, so it's relatively difficult to answer. But like I showed, the results look quite good. So for the materials we've investigated, so I guess it's okay. But again, I mean, there are materials in which we know that non-diabaticity is something quite important, where you have so for example this case of this doped diamond and so on, where you get phonon softening and things like that. Then in those cases it would be important, yes. Okay. But those are doped material, and I mean heavily doped. And this boron nitride is like, I don't know, 0.3 or 0.4 eV down doping, so it's quite heavy doping. And in those cases, yes, it would be important, I think, yes.
All right, thanks a lot.
Yeah. Okay. A couple of questions.
Thank you for the talk. So can you go to the two-photon slide that you had? Yeah, thank you. To me, it looks like that the effect here is actually quite erratic. So I was wondering, like, do you know, like, what would I be looking at if I want to say, like, beforehand to try to guess if the effect is going to be strong or not, or people not?
That's a very good question. So the author of this paper, to my knowledge, only looked at gallium arsenide, and gallium arsenide, the electron mobility of gallium arsenide is very specific. So the effective mass is very tiny. And so for that reason, I think it's a case where you have a lot of those cross scattering, because you have such a small effective mass that you have a lot of those. So I would guess that this is stronger in small effective mass material, but I mean, it hasn't been, as far as I know, it hasn't been investigated in any other material than gallium arsenide. So, I mean, I cannot say, but based on the fact that it works well for other materials, I mean, it's true that gallium arsenide is very difficult to describe, because DFT doesn't do a good job at describing the effective mass. It's so small that it's very tough. The electron, so the hole is fine, but the electron effective mass of gallium arsenide is very tough, very sensitive. Yep.
almost always. We have the equation that we want to adaptate to about specific anomaly. So some of these things are not anomaly. For Phonon, there are only approximations for maybe let's say 4. Okay, it's almost perfect. Because there are some cases where it fails. So those are anomalous cases. And the fail is some portion of the given job, not only that. So usually single still. So what's the theory is that we say failure. So it's interesting to discuss this anomaly. So for systematic method, you have to store things that
So yeah, hopefully everybody. The mic is a bit problematic, I guess. But
Thanks for the talk. I have a question about comparison between acoustic and optical for contribution. So
Yep.
I guess materials showing large contribution from optical moment are those like a polar material to and in that case, how do you calculate the scattering rate? Is it like I guess do you consider something above the deformation percent?
above what?
Beyond deformation percent? Like what are
No. Sorry. So maybe that was not clear. Here we treat everything. So this is fully ab initio. We treat all modes at equal footing. It's all. So this is all included. So when we solve the equation, yeah, that's a very important point. So when we solve the equation, maybe this one here, we really include all the Electron-Phonon. We include all modes. The phonon frequencies are included everywhere. So everything is included. I'm just saying what I was saying is that people have been trying to avoid computing the Electron-Phonon matrix element ab initio, and they've used model to describe the Electron-Phonon matrix element. And so there are some models like deformation potential in which you sort of approximate the Electron-Phonon matrix element with a model formula. So it's a model with some parameter. And so deformation potential is a model that can describe relatively well acoustic mode, but it doesn't describe optical mode. And so what I was pointing out is that you also have like Fröhlich models to describe the optical mode. And so you could try to add all those contributions, do many different contributions from many different models. But what I'm saying is that you need to be careful when you're using those models, because in some material you have a contribution from acoustic, optical, and everything, and therefore having a fully ab initio calculation that doesn't have model, it's really fully ab initio, that's quite valuable, because then you don't have to rely on approximation that might, or models that can work only in certain situations. So like deformation potential might be able to describe well those material, but it will fail in those. And if you use Fröhlich sort of description, Fröhlich model, then you will be able to describe those, but not the other one, and so on. So what we were trying to do here, like Luciano pointed, was really to have something that works in most cases and without having to think about which model to use. So it's just use the code. There's no parameter, you just run the code and that's it. And it includes everything. Yeah.
I think it's time to move on. Let's thank Samuel again.